phase encoding. Okay, so the last lecture I said was the most important one for really understanding how the image is created, just in a physical sense of, like, what's actually going on in the brain when you turn the gradient on. And what's actually going on in the brain when you turn the gradient on after you've done an RF pulse is you're making these, what I call stripes of spin phase. So you're causing by turning the gradient on, you cause the precession to happen at a higher frequency, but that's not that's how the thing works. But don't think of it that way. Think of it as what you're doing is you're creating these 360-degree stripes of spin phase across the brain. So that's the critical feature of how you generate a Fourier transform of the brain. And so if you just write up that Fourier transform once again, so you have a complex valued signal for a particular spatial frequency, and let's just like directly sort of relate the Fourier transform to the physical things. So you're summing across all x of a piece of the brain, and then you're multiplying for each x point in the brain, you're multiplying it by these stripes, and this thing is basically kx across all little chunks of the brain. So this thing right here, this thing is an angle. That's the angle of the stripes. And we can code that angle as a sine and a cosine, the real and imaginary part of it. But where does this come out of? This comes out of the RF coil, which is doing phase sensitive detection. That's how you get the complex part of it, because it's got two dimensions. And then what's doing this sum? The RF coil is doing this sum. So the RF coil is doing the integral across the entire head. And what is it integrating? It's integrating, basically the proton density at point x in brain. So there's one x point, but we've got to do all the x points. And then what is this thing? These are the stripes. So, these are it's basically for each x, there'll be a different amplitude 1 component that has a real and an imaginary part. So you can, and the real and imaginary are cosine and sine. And so you can either think of it as like a two-dimensional thing or just separately as a sine and a cosine. And so what is that? That just is cosine of 2 pi kx. And notice that the minus doesn't affect it because cosine is symmetric. So if you're, cosine of minus 2 pi x is going to be the same thing as cosine of 2 pi x. But the sign does get affected. So the y component does get affected by the sign on the exponent. So this thing here, that negative only ends up affecting the sign, not the cosine. So these are basically the stripes. These are basically the stripes. And why are they stripes? Because you go to each point in x, and so you have to increment x. And so depending on what, spatial frequency, for a given spatial frequency. So that's just the direct phase sensitive detection. It's supposed to be PSD. So that's the direct correlation between, the actual signal coming out of the RF coil, a proton density at a point in the brain, and then you're multiplying by stripes, and the stripes are stamped on there by the gradient. And then you take a snapshot of that phase setup, stripe phase setup. And how do you actually do this multiplication? This thing is a complex multiplication. Complex mult. How do you do that? You basically do that just by having varying amounts of proton density. And so obviously if there's less proton density at a point, that real number, your brain is real, is going to change the amplitude of the stripe at that particular X point. And so that's how the actual complex multiplication is done. And then it will basically change the length of this unit 1 vector that this thing has, depending on how much proton density there is. So it's very directly related. And how is this normally done? This is normally done, you turn the gradient on in the negative direction, and then you turn it on in the positive direction. And so this is like, gradient x. And what does that do? Well, we've done an RF pulse somewhere back here, and so there was an FID. But then what happens is you get an echo. You get a gradient echo, like there. And what is that gradient echo? Well, that gradient echo it starts off at, k equals minus 128 over here. And then when you get right to the middle, that's k equals 0, no stripes. And then when you get out to this end, you're up to k equals 128, say. So what does that 128 mean? That means just the number of stripes across the brain going in the x direction. So now you can finally sort of put together this picture of the echo, because we were mainly just talking about like what is the amplitude of the echo when everything's back in phase. But in fact, we're using the entire echo. So this is where we sort of finally put together the echo with the the block equation decay together with the echo. We're actually using the entire echo when we record MRI data. Okay, so now the plan is that's good for 1D, and so the question is how do we actually do a second dimension of stripes, and that's what phase encoding is. And so since there is no frequency encoding and we already understand phase encoding, then all we got to do is just do another dimension of phase encoding. And the trick to understanding this is they're both doing the same thing, but how could they both do the same thing and not interfere with each other? That's really the curious thing. So how do they not interfere with each other? Because they're both affecting the spin phase through the entire brain. So the only difference between frequency and phase encoding is strictly which gradient is on. That's the only difference, only fundamental difference. So the gradient is on in one direction, and then the gradient is on perpendicular to that direction for the phase encoding. So to get through this, let's just draw out the whole pulse sequence in a little more detail, so that we make sure that we know what's correlated with what. So the first thing we have is the RF, transmit, and so here's our little sync pulse. And when we're doing the sync pulse, we turn on the Z gradient. So we go down to here, turn the Z gradient on. That's because we want to select a slice. And then we have to sort of fix it afterwards. That sort of fixes the problem the dephasing that we caused by turning that on. And then here's the phase encode direction. And so what we do on the phase encode direction is we turn on a bunch of different levels of the phase encode direction. And what the meaning of that is, the meaning of this symbol is, do this whole thing over with all different settings of the phase encode direction. That's the coded meaning of that little symbol there. Now, let's just go back to the slice select. Isn't the slice select making stripes? It is. So when you turn on the slice select, what happens is it's making stripes in the z direction. And then spin phase stripes, because it's causing spins that are at the high end of the gradient to oscillate more rapidly. But then this little fixer sort of like puts them all back. So it makes a whole bunch of stripes by the time you're done selecting a slice, but then the little fixer sort of unwinds them all and puts them back all flat again. Now notice, you can turn this one on at the same time as the fixer. So while you're in the process of unwinding all the stripes that you unintentionally or didn't want to create by the slice select, you're actually winding up stripes in the y direction. So you can do them, we'll see how magically they can sort of somehow appear to not interact. They actually are interacting. So every gradient affects every spin in the entire brane. So it's not like they're not actually directly affecting the spins, because remember the gradients affect the z component. So the z component, the z gradient changes the z component in the z direction, the y gradient changes the z component in the y direction. So they're all affecting the same thing, the z component, and so they have to somehow interact. Okay, so then finally we'll put in the one that we did last time, which was the, what they generally call the readout. And so here's where we go like that, and then usually we turn the gradient on a little bit, twice the amount of area, but a little less high, so we can read out the signal over a little bit bigger amount of time. And then what do we get out of that? Well, right when the RF pulse happens, you get a big FID that you're ignoring, and then here's where the gradient echo occurs, like that. So what are the main, and then we at some point do it again. So let's say we do it again here. So here's our, if it's a gradient echo, there's like a not, etc. So we just do everything exactly again. And so what are the main times here? So the main times are this time, which is the TR, and then this time, which is the TE. Okay, so, and then, last but not least, we actually record the data. And so what is the data that we actually record? We don't record that first one, and so here's where you're actually recording data. These are the snapshots of the spin stripe. So this is, record. So we only turn the recorder on during the echo. So that's our basic sequence. So this guy was the slice select. This one was the phase encode direction. And this was the quote frequency encode, which is just phase encode in a different direction. So those are really the only difference is the direction. So this is RF record down here. And remember back on we mentioned that this distance here between the data points, that delta t equals 1 over the bandwidth, or you could say the bandwidth equals 1 over why don't I write it the other way? It's a little more intuitive the other way. So basically the bandwidth equals 1 over delta t, and delta t is this thing here. Just the time between data points. And remember, lower bandwidth, meaning like more time between the data points, was better signal to noise. Okay, so now let's just draw a picture of the actual, what's actually going on in a slice. And so we're looking down on a slice, and what we're going to be looking at is the spin phase across the across the slice, sort of looking down on the slice. And we'll have the phase encode direction going in the y direction and the frequency encode direction going in the x direction. So let's make a bigger one than last year, so I plenty of space for the stripes. Okay. Okay, so I'm going to draw it at 2 different time points here. So let's start with the first time point. So basically you do the phase encode before you've recorded any data. So you do the RF pulse and then do the phase encode. Let's just forget about this sort of rewinder thing and just concentrate on the phase encode. So what's the phase encode going to do? It's going to wrap up stripes in a y direction. So what that means, so say let's just do y spatial frequency equals 4. Okay, so this is ky equals 4. So there'll be 4 stripes, and the way I was drawing them was, if you look in the notes, this is a dark line, and dark sort of means, small. So there's basically a ramp of spin phase. And so what does that mean? It just means like the little vectors right here are pointing towards 0 degrees, and then as you slowly go across the stripe, then they point 45 degrees, 90 degrees, 180, 270, back to 360. And so when you get up to the top, it wraps around. And so I'm drawing out this circular variable as an actual, sort of color. And so it's not, that's one problem with circular variables. It's hard to sort of illustrate them with a single color because you're going to get these sharp edges where they wrap around because 359 wraps around to 0. So here's the 4. So the idea is we turn this phase encode gradient on whatever amount of time, because remember it's a combination of how long the gradient is on and how strong it is. So we basically just turn it on for however long we need to get exactly 4 to make the ones at the top end of the gradient, say this was the top end of the gradient, get 4 ahead. So if we plot out the phase, so here's a graph of the phase, and say this is 0 and 2 pi, so 360 here. Then what does that look like? Well, it just looks like the phase goes from 0 to 360, and then it goes back to 0 to 360, and then it goes back to 0 and 360, like that. So that's basically what I've tried to draw there. I just tried to draw the phase. So this is the phase right there. So what is that? That's basically, and what if we look at the phase going in this direction? So here's 0 and 2 pi. Well, it's all 0. So it basically just, it's just along the, nothing's changed no matter where you go. Okay, so what is that? That's ky equals, or say, I'll start off at kx. So that's spatial frequency x equals 0, and spatial frequency y equals 4. And somebody asked, I remember last year, somebody asked, well, what are the units of spatial frequency? So let's just go back, like, what are the units of, what are the units of temporal frequency, like cycles per second? You have to have some kind of, thing underneath. So, if you think of, cycles per second, that's how we have temporal frequency. And you don't have to do cycles per second. You could do cycles per hour or cycles per minute. So what is spatial frequency? So that's temporal frequency. Spatial frequency is also cycles. It's still angle, but it's basically cycles per distance. For example, centimeters. Or the one I'm using here, which is slice width. So you could do cycles per centimeter, or what I'm doing here, the units I'm using here are cycles per, how many cycles do you have across the entire width of the slice. So once again, just make sure we know what we're looking at. We're looking at a little slab. We excited a slab like this. So here's that slab, okay? So we're, looking down on slice. So we're looking down at the slice, and we're sort of imagining what the spin phase in the physical 2D stripe, 2D slice actually looks like. So those are the stripes, and so the dimensions here. So that's actually y, and that's x. So this is real space. So these are the stripes in real space. Okay, so now, for the time being, we're ignoring, we'll just ignore this little pre-winder. I'll draw the whole thing out at the bottom here, but let's just ignore this guy for the time being and just assume we didn't turn that on, and we just turned on the frequency encode gradient. So now what happens, so that phase encode gradient, all this happened before we did any recording. So we did the RF pulse, but we haven't done any recording yet. And we haven't turned on the, if we throw this one away, we haven't turned on the frequency encode gradient. So now we turn on the frequency encode gradient. And so now the problem is, isn't that going to mess up all of the spin phase? And the answer is yes, it will affect all of the spin phase. So let's just make sure I got the right width here. There we go. Okay. So here's another picture of the slice. And so now what happens if let's say we turn on the frequency encode for long enough to get up to 10 stripes. So there's going to be 10 stripes going across. So this should be 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you got 10 stripes going across. And let's say we haven't done anything else with the phase encoding gradient. It's off now. And so we still have 4 stripes going in this direction. So here's the 4 stripes going in this direction. I need these little marks so I can make my stripes in the right direction. Okay, so what do the stripes look like now? Well, now they're going to be tilted. So they'll be tilted like this. So here's some tilted stripes. So why do they get tilted? So they got tilted because the gradient basically just adds additional phase everywhere throughout the entire brane. So when I turn on the Y gradient, it's not like it's going to not interact with whatever happened to the stripes from the X gradient. It does interact. So if you work it out, what you can see is going to happen is it's going to cause the stripes to rotate. So that means that at a particular point like at this point in the brane, this guy used to be 2 ahead if you count from the top. At this point, this guy's going to be a lot more than 2 ahead because it would have been wrapped up by the X gradient. And so why is that? That's because each gradient affects the same thing, the Z component. And so whenever you turn a gradient on, it's affecting all the spins. So how on earth can they not interact with each other? So the trick is, if you just go down in this direction, you still got 4 stripes. So just look at that. So there's still, no matter where you go, as long as you go directly in the y direction, you only got 4 stripes. So you haven't actually changed. So if you decompose that phase into its sort of x and y components, you still only have 4 stripes here. So you haven't changed that, but you definitely have changed the phase in this direction. So here's 2 pi. And so now what we're going to get is, we're going to get 10 stripes. Etc. So we have 10 stripes in that direction. But as long as we just go in this direction, we still got 4. And likewise, no matter how many stripes you put on in the y direction, it doesn't matter. If you go in the x direction, you'll only run into 10 stripes. So the trick is, it's not that the phase encode gradient and the frequency encode gradient are not interacting with each other. They are. It's just because of this, the way the circular variable works. And as long as you're sort of going in a perpendicular direction, if you just count stripes going in the y direction, the number of stripes in the x direction doesn't affect it. Now, it does affect the number of spins. So let's take, like if we take this point right here, so we take that point right here. So let's just look at that point. So at this point, and then let me just annotate this last one. So this is kx equals 10, ky still equals 4. So let's just look at that little piece of brain there. So how much are these ahead? They're 2 ahead. They're 2 ahead of what they would have been if you hadn't turned any gradient on. And what about this guy right here? So this is a lot more than 2 ahead. So this one is 1, 2, 3, 4 plus 2 is already 2 ahead from here. So this guy's 6 ahead. So that just shows you actually did affect all the spins. But if I count how many times I'm ahead just going in the y direction, I only get 2. So here, I'm not ahead at all. Now I'm 0 degrees there. Now I'm 1 cycle ahead. Now I'm 2 cycle ahead. In reality, that actual spin is 6 ahead. And so you can see that the angles just add, just like you were doing with complex multiplication. And you'll see that when we look at the 2D Fourier transform, you can see that the angles for the x and the y just add. That's how it works. Okay, so I didn't draw it. Let me just draw in the spin phase stripes. So here we've got, this is where there's 0 phase here. And then you can see, and then, so if we go across the stripes sort of in a diagonal fashion, you notice there's more than 10 stripes. So if I go across in the x direction, I only get 10. But if I go this direction, there's more than 10. You can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 stripes in that direction. But if I just go in the x direction, then I just get 10. So I'm just trying to color in the spin phase here, etc. So that's basically how phase encoding works. It's just exactly the same as frequency encoding. Only difference is we're just going in a different direction, just using a different gradient. Okay, so stop just for a second and just ask for a question or two. How's that going okay? So we haven't written up the 2D Fourier transform yet, so you can see that it just relates very concretely to this. You just add the phase, you add the angles from the x and the y part together, just like we're doing here. We just added 2 plus 4, so this is 6 ahead, equals 2 plus 4. So when you look at it this way, you can see that it's, there is nothing mysterious about phase encoding. It's just the same as frequency encoding. Okay, any questions? Now, what I want to do now is draw out what actually happens when we put this little pre-winder. So we call this one pre-winder. So what that does is that wraps up all the way to like 128 stripes in the negative x direction. So it actually sort of makes negative frequency stripes. And what are negative frequency stripes? Well, you could turn the gradient on either way. You could either make people get ahead or people get behind. If you make people get behind, that's a negative frequency. It just depends on what direction you're wrapping the little spin phase stripes. And it's perfectly reasonable to wrap them in a negative direction. And in that case, to get back to 0, you'd have to wrap them in a positive direction. And that's what we're doing. What we're doing right here. So if we draw that out, let's just draw out the echo, so that we see exactly, what we're talking about. So I'm going to expand this. So let's just take this thing here and expand it out there. Just that little readout bit. Oh, sorry, no. Yeah, so starting after we turn the pre-winder off. And so what you're going to have is this long echo, because you're actually starting to record it right here. That's supposed to go right there. So we turn on the recording right after we finish our pre-winder. So what's going to happen here? Well, we've turned on, let's just say, 4 stripes in the phase encode direction, and then we can do it at the same time. Actually, we're causing negative stripes in the x direction. And so what does that do? That sort of generates this big echo. So here's our echo. Sort of looks a little sync-like. Something like that. And remember, it's going to have there's phase-sensitive detection, and so basically there's going to be a second number here. So you get two numbers out of your RF coil. So there's the second number. You got, this is our, this is our imaginary, which is not imaginary at all, and then here's our real number coming out of our RF coil. So that's this whole sort of echo drawn out. But what is the spin phase situation look like? So at this end, what we would have done is so let's draw six guys. So first, let's put the middle one in. So what happens at the middle? Well, at the middle, we would have used just the amount of gradient to completely cancel out the stripes that we made here with this pre-winder. And so what's going to happen in the middle? Well, we're just going to end up with 4 horizontal stripes. So what is that? That's kx equals 0, which is the echo center. Ky equals 4. But now let's go back to the beginning. What's going to happen here? Well, we're going to have 4 stripes in the vertical direction and 128 in the x direction. And so what will that look like? That will look like something like this. So there'd be a whole bunch of stripes in that direction. But if we go in the in this direction, we should only run into 4. So they'll be almost vertical looking like that. And then, so what will that be? That will be, kx equals minus 128, and ky still equals 4, because they somehow don't interact with each other magically because they're in different directions. And then what will happen is we'll slowly sort of unwind these until we finally get back to no stripes in the x direction, but still 4 in that direction. And then we'll start winding them up the other way. And so they get closer and closer together until we get all the way up to the very end where there's like a zillion stripes. So that's when I first was trying to understand how this worked, I didn't get the impression of like, wow, there's a lot of stripes. They really get up there. They get up, so you've just microscopically twisted all the spins, to make all these perfectly straight, well, assuming the gradients are completely linear, perfectly straight spin phase stripes across the brain. So this is, here's our data point collection, right? So our data point collection is going to just take snapshots of this. So here's all our data point, collection. So we just go up and then just take a snapshot of whatever the real and the imaginary is. So that's basically how you code a slice. So you need a lot of data because this was just for a single, so we just gave a single example of, say, ky equals 4. So we just did one. We just did one of those, but we've got to do 256 of these. So you'll have to do, start off with, a really strong gradient. That would be plus 128, go down to 0. So the 0 is a special case. So when you have kx equals 0, ky equals 0, you got no stripes. So there's a single data point, the center of k-space, very important point, that has 0 stripes. In this case, we've still got four horizontal stripes because we did ky equals 4. But if we do ky equals 0, we'll end up with, kx equals 0, ky equals 0, and that's no stripes. Also known as the echo. That's the strongest signal that comes out when there's no stripes, because as soon as you put on stripes, you're getting people out of phase with each other, T2 star decay, and that's lowering your signal because it's causing different spins to be pointing in different directions, and so they cancel each other out when you do the vector sum. Okay, so how does the scanner help you? So if you sit on the scanner and you say, like, I think I'm going to change the TE, think of what has to happen. So if I change the TE, say I make this a little bit longer here, well, what's going to happen? Well, a whole bunch of different things are going to happen. I'm going to, let's say I keep the bandwidth the same and increase the TE. So that what that means is I'm going to sample the same the same spacing of data, but with a longer TE. Okay, so this was, same bandwidth, longer TE. Now, you might wonder, well, then you might run into TR, and so the scanner interface might say, oh, sorry, I can't do that because I've got to lengthen the TR in order to give me enough time to move the center of the echo to a longer time. But you can also change the bandwidth, and what happens if you change the bandwidth? So let's just keep the same TE, but a lower bandwidth. So a lower bandwidth meaning like more spacing, so you know, a lower bandwidth means that the delta t number had to go up. So let's keep the same TE, but so here's the original TE, and here was our new TE. So here was you know, this was TE1. This guy was TE2. But what if we keep the same TE but a lower bandwidth? So that would be, let's keep the same TE but a lower bandwidth. So now what we need to do is spread out our data collection. So now we can't go before the RF pulse, but basically what we want to do is just spread out our data collection over a longer period of time like that. So now we've got the same, and we're back to the same TE here. That's just TE1. Back to the same TE, but we've spread it out over a longer period of time. And so what is that? That's same TE, lower bandwidth. So that's what's actually happening. You can see it's quite invasive. If you change the TE or change the bandwidth, it's just moving all these things around. And how does it move it around? Well, it's got to change the strength of the gradient, because you have to turn the strength of the gradient down in order to collect data over a longer period of time, because you don't want to spin phase stripes to wrap up as fast. They need to wrap up a little bit slower so that we can collect the data over time. And you can see at some point you're going to run into the wall, like, oh, the TR is too short. I've got to extend it. But also, alternatively, you could say, let's turn up the bandwidth, record the data really quickly. Maybe we could scrunch the TR down. So the pulse sequence on the scanner, when you change parameters like that, is doing all these tweaks of the pulse sequence to make it look completely different, just depending on exactly what thing you typed in. And so that, and the software will, you know, prevent you from doing something that's impossible and sort of warn you. But the thing is, if you don't realize what's going on down in the basement, it's kind of like, it's better to know what's happening. Okay, so that was our phase encode and frequency encode. And so now let's just put up the 2D Fourier transform so you can see it's actually not very different than the 1D Fourier transform. So here's our signal. So now our signal has two different spatial frequencies in it, so kx and ky. So it's a two-dimensional. So this is 2D Fourier transform. And so it's got two different spatial frequencies in it. And so now we have to do a double integral. And what is a double integral? It just means do what's on the right here for every possible combination of x and y. That's all a double integral is. So for every possible combination of x and y values, sum up the following thing. And so now what we're summing up is a two-dimensional image, x. So it's got x and y, and then we're multiplying by two-dimensional stripes. And so what's a two-dimensional stripe? It's just a stripe that has kx times x plus ky times y. So that's basically a 2D stripe, and then we're summing across dx dy, meaning like for each little two-dimensional voxel, each pixel. So you can see you're just adding. So we could have written that out as, e to the minus I 2 pi kxx times e to the minus I 2 pi KYY. But if you have this, if you're putting something to the same sort of base here, you can just turn that into adding the exponents instead of multiplying. So remember what we said. What's complex multiplication? It's basically just multiply amplitudes and add angles. And here you can actually see you're just adding the angles. So these things are angles. This whole thing here is an angle. So that's all there is to a 2D Fourier transform, and you can obviously do a 3D Fourier transform also. So let's just briefly introduce that idea. So we could just tack in a z here and make a three-dimensional Fourier transform. So what does a 2D Fourier transform look like in actual space? So in actual space, what it looks like is you did a slice select pulse in order to select a little slab like that. So a little slab of brain or whatever, knee. And then once you've got that slab, then what you did was you put stripes on it. So here's some stripes on the slab like that. And then all we have to do is just put all the different possible combinations of stripes on the slab. And so, we have to put them like that, and you put them like this, then all the different possible spacings. So for one slab, what is that number? Well, it's somewhere on the order of, say, 65,000 different stripe patterns. So if you consider you have from 0 to minus 128 plus 128 in spacing, but then you've got to try all the different orientations of them also. And so you'll end up with, so the total number of data points you'll collect will be 65,000 data points just for one slice, But what people, so that's our 2D, but people, then thought, well, why stop there? And when I first read about 3D sequences, they said, well, this was back when I didn't understand how MRI worked. They said, well, all you need for a 3D sequence is a second phase encode direction. And when they said that, I said, what? Yeah, it didn't compute. I thought we had phase and frequency encoding. How could you just arbitrarily have a second phase encode direction? It doesn't make sense. Aren't you cheating? Wasn't there supposed to be just frequency and phase? But then when you understand that actually there is no frequency encoding, and frequency encoding is just another phase encoding direction, you already got a different, so you basically add a third phase encoding direction. And so what does that look like? So in that case, you don't just excite a slice, you excite the entire brain. The RF pulse hits the entire brain, and then what happens is you end up with some weird combination of stripes that are sort of going across, they're going across all the planes in the brain. So basically, there'll be tilted stripes. They're tilted no matter what face of the cube you look at. So they'll be like that. So stripe madness. And so now you got a whole lot of stripes. You got 10 million stripe patterns. So you've got to do all the different spacings, and then you have to cover all the different orientations of all those different spacings. And so that will be for example, 10 million. So here, this would be for example, 64K, 64,000. So this is a really good way to collect data, and virtually all structural scans are done this way. And the reason is because, well, there's a couple reasons, but one reason is you get data from the entire brain So don't forget where, the brain is in here. So this is real space. It's real space in here. So you get data from every point in the brain for every RF pulse. Whereas here, you're only getting data from just this slice, and then you have to separately excite another slice and get data from that one. And so the signal to noise is going to be a lot better because we're essentially getting every single RF pulse is giving you data from the entire brain. And so this allows you to make much smaller voxels and go much faster because you have so much more signal to noise. And so that's why we do this. We haven't done this yet with functional imaging. You can do it with functional imaging, and we'll talk about that, partly because of motion problems. But for structural scans, this is completely standard. So that's the plan. So you can actually put sort of like volume filling stripe patterns on the brain, in addition to just putting them onto a stripe. And all you'd have to do to this equation is just add another dimension. What would you have to do to the pulse sequence? You just have to, if you wanted to make a 3D pulse sequence, you would just have to tack on a whole bunch of different Z phase encode steps. So you'd have to do for every setting here, and then in an inner loop for every setting here, do this. Okay, so let's stop for a second here. And any questions? It sort of makes sense now. And you can finally put everything together. Like here's the echo. You're actually recording. So the whole echo is changing spatial frequency as you go through the echo. And so you record the entire echo. Why do we concentrate so much on the center of K-space? It's because that's the one that most strongly affects the way the overall image looks. But in fact, to make the image, you've got to record the entire echo. Okay, any questions back? Stripe questions, basic stripe questions. Got to be one or two questions. So it's phase and frequency encoding. It's basically the same thing. It's affecting the spin phase at every point in the brain, and the only difference really is just, you're applying the gradient, which is affecting the Z component of the B field in a different direction. And it's not that they don't interact, they actually do interact. It's just that if you count going along the Y direction, whatever you do in the X or the Z direction doesn't affect you. It doesn't affect the number of wraps of spin phase that you'll encounter, no matter how many stripes you put on in a different axis. And so that's the trick. Okay, got to be one little question there. Sorry, I didn't leave any space earlier on for questions. So I'll just say, question? No question? Okay, we'll just say one final thing. So what is fundamentally a Fourier transform? It's basically just the sum of stripes, right? It's the sum of weighted stripes. So this weights this stripe. And how does the inverse Fourier transform work? The same way. And so what are you doing? You're just actually constructing a brain out of uniform stripes. And it's very similar to something like, you've got an orchestra with bass drums and cymbals and violins. You've got this complicated signal, across time, and then we do a Fourier transform of it, and what does it do? Well, it turns it into a stripe that goes across, and then another stripe that goes completely across the whole time that you recorded the orchestra, and another stripe that goes across the entire time you recorded the orchestra. And you can get back this signal just by adding those guys up, even though they're completely uniform across all time. And that's what we're doing here too. So that's actually how the reconstruction works. You just take a bunch of weighted stripe patterns. They could be three-dimensional ones, but just think in two-dimensional. So you just got like stripes that extend across the entire slice, all different orientations, all different spacings, and different brightnesses and different phases, because the exact placing of the stripe is all different. And that's what the phase tells you. And so how are you making an image out of the brain? You're just adding together these stripe patterns that extend across the entire image, weighted with a particular phase. So remember when we said the way the Fourier transform works with a real image is all the imaginary parts cancel out. And so you can literally make an image by taking little sinusoidal variations in brightness across, like if you printed them onto transparencies of different orientations and different spacings and different brightnesses and different offsets, and just add those real numbers together, and you can get a face. So you can take these uniform stripe patterns across the entire image, add them all up if they've got the proper phase and the proper weighting, how bright the bright part and the dark part is. That's the weighting. That's the weighting right there. Then you can actually see a face out of that, just like you do with an audio signal. So that's really the concrete way. We're stamping these stripe patterns onto the brain, recording all that data, and then basically just reconstructing the brain from stripe patterns, because the inverse Fourier transform is the same as the forward Fourier transform. Okay, I don't know if that probably didn't help, but any final questions in the last minute about phase encoding, or the second phase encoding direction, which is actually the third phase encoding direction. Sort of seems somewhat understandable how you could actually get an image. And now you can see it's a feature that every data point comes from the entire head, because that's actually what we want. It's exactly what we want. We want to essentially sum across every point, every XY point in the slice. Questions? Stripe questions? Yeah. All good. Okay, I guess I'll call it a day. We'll end it there, David.